Hi everyone. Welcome to supplementary video 7. And this video is basically about an example problem on similarity transform. So in lecture 6, we discussed a similarity transform example. And I wanted to give you another example, which is slightly more challenging than the one we discussed in the class. And this example is very relevant because we will do a slight trick which is also important for you to do your homework problem in homework 2. So let's discuss this problem. This is an example in the book, example 4.2-2. And what basically the problem says is that we have a system. So similarity transform, as we have discussed, we will be basically focusing on 1D unsteady problems. 1D unsteady problems. And in this problem, what we have been told is that there is a mass of solute. There is a mass of solute that we are basically putting in a system, which is a semi-infinite system. So let's say this is Ca, this is X. So this solute can diffuse throughout, but the total mass in the system remains the same. So we have been told that Ca dx minus infinity to infinity is constant as m. So this has been given in the problem. And what we have been asked to do is basically find the concentration profile as a function of x and time. So there are two variables. It's an unsteady problem. So with time, what is happening is that basically with time, so as the time increases, initially it was a narrow peak, it starts to diffuse out and it starts to become broad. So this is the problem that has been given to us to solve. And the challenge in this problem is that first, it has both space and time. So of course, it's not like, a steady problem. It is an unsteady problem. And the second thing is that there is no concentration anywhere. We just have been told that concentration at x is equal to infinity, or we can assume rather is zero, because if solute has been started somewhere initially, it will basically take infinite time to go, to the other side, or to infinity essentially. And but we don't have a concentration scale essentially, and there is no initial condition provided. So that's a challenge. So there is no initial condition provided to us. So one thing we can do say is that due to symmetry, there is symmetry at x is equal to 0. So in terms of boundary conditions, we can say dc by dx at x is equal to 0 is equal to 0, and concentration at x equal to infinity is 0. But we still don't have any concentration scale. All we have is the total integration of the concentration is m, or there is no initial condition rather. So this condition kind of essentially becomes like an initial condition. It is not an initial condition. It will just replace the initial condition. So first thing we want to do is we want to write the governing equation. Um, governing equation, and the governing equation essentially in this problem is del Ca by del T is dA del square Ca by del x square. Okay, and this is because it's only a function of space and time, and there is no reaction, and so that's why we basically get this equation. And the boundary condition I started a little bit earlier is that x is equal to infinity, the concentration is 0, because it can never really reach infinity. If we start with some solute, it can never really reach, and at x is equal to 0, it is symmetry. Okay, and the initial condition is not there, and this kind of becomes like a proxy initial condition. Okay, so this is the problem, and now how do we solve it? So one thing we can see is this is an infinite system, so there is that nature in the system. And when we discuss the problem, we discuss that whenever there's a semi-infinite or infinite system and it's one space and one time, then it makes sense to think of a similarity transform. So that's what motivates us to think of this as a similarity transform. So what we want to do is we want to find the variables. So first we want to define theta, right? And theta is something very dimensionless concentration that goes between 0 and 1. That's our goal. Now here there is no concentration scale, and that's the problem. So so we can say, okay, theta will be some Ca, but what should I divide this by? And that's a challenge in this problem. So one thing we can note is that there is something which is basically decreasing with time, and that's the concentration at x is equal to 0, and that's the maximum concentration we will get will always be at x is equal to 0 because it's always diffusing out towards infinity. So this is, let's call this Cm, and this is a function of t. Note that we do not know the Cm, but we can say that this theta is Cm of t, so that theta always remains between 0 and 1. So that's the goal. That's the first goal, is always to find something which is between 0 and 1, and so this is Cm of t. Now note in the class what the problem we did was, it was Ca by Ca naught. So we all the denominator was constant, but here the denominator is a function of t. And as you will see, this will become slightly will make our problem slightly more complicated. The second thing is the eta. And right, how do we define the eta, which is a similarity transform variable? The similarity variable. And this is the dimensionless concentration. So how do we find these two? So in dimensionless concentration, we have defined, but we still do not know Cm. So to get both of them, what we will do is we will simply say we will do the order of magnitude analysis. Order of magnitude analysis. So let's first do the order of magnitude analysis on del Ca by del T. So it becomes delta Ca by T becomes Ta delta Ca by delta square. And this is something we have discussed before, that delta square is the penetration depth, or the distance basically that will feel the effect of concentration change. And this will give us that delta is root DAT. So when we are thinking of our similarity variable, we want to basically do something like x by delta. This is exactly what we did in class, and x by root DAT. So this does help us a little bit, that we are able to, solve this and get this result. But what we do not know is the Cm. So the similarity transform variable remains the same, but we do not know Cm. We know it is a function of time. And to do that, the second thing we can do is we can do also an order of magnitude analysis on the initial condition proxy or this integral equation. And this is something we have not discussed in detail. So when we want to do an integral, what we want to do is we want to say that our equation here is minus infinity to infinity c of x comma t dx is equal to m. You can simply approximate this as some sort of Ca times delta x is equal to m. That's how you typically do it. And the concentration scale here is, we don't know the concentration scale. So the only obvious scale that we should take is the Cm. And delta x is simply delta, right? Or Cm is equal to m by delta or m by root of DAT. Okay. So this is what we did. So I hope this makes sense. So we started with the problem. We said, okay, this is the governing equation, unsteady diffusion, and this is some sort of total mass being diffusing out to infinity, where infinity will have no concentration, and then there is symmetry. So we defined it, and we said this is a proxy for initial condition. Because this was an infinite system and 1D unsteady system, similarity transform is a natural choice. And to do that, we said we will define some concentration scale Cm, which we don't know, which is the maximum concentration or concentration at t equal to 0. And then, concentration at x is equal to 0. And then the similarity variable remains the same because our order of magnitude analysis gives us the same penetration depth. And the other thing was that now we have also done order of magnitude analysis on the integral equation to essentially find some sort of Cm scale. Okay. So now finally we get theta is Ca by Cm, or we get Ca into root DAT by m, right? And eta is x over root DAT. Okay. So this is what we get. Now what we want to do is we want to basically substitute and go back and try to substitute into the original equation everything in terms of theta of eta. So we want to now write everything in terms of find ODE for theta of eta. This is our goal. Okay. So let's start with the first term. So first equation is del Ca by del T. So how should we go about the theta of theta is, we will first write, note that CA is theta times m by root dat. Okay, from this equation, this is what it is. Right? So which means that del CA by del T, which implies that del C by del T is del by del T of theta times m by root dat. Okay, so this is what you want to find. So del C by del T is del by del T of theta times m by root dat. And this essentially becomes, so we have two terms with respect to T, one this and one this. So we'll apply a product rule. We can take m out. So we can say d theta by d eta. And as we had discussed in class, you will become a bit more familiar with time about how to take these product rules. Del eta by del t. So this is d theta by d eta dt essentially by doing a product rule, and then 1 by root dat, right? And the second term becomes theta times uh, 1 by root dat minus 1 by 2t. So, or essentially, you can say, you can just do a minus sign here, right? So what I've done is minus half t raised to the power of minus half, and then I've decreased, this is the derivative of 1 by root dat, and theta is then multiplied, okay? So when we do this, essentially, and we should note that del eta by del t, so eta is x by root dat, and del eta by del t is minus eta by 2t. Okay, so you take that full same expression and you then just take a half times t denominator. Okay, so this is what we know. So you can substitute this back here, or essentially del c by del t. And I encourage you to try this. So this takes a bit of practice, but I'm sure you can get this. Becomes m root dat times 1 by t d theta by d eta into eta plus theta. Okay, so this becomes del c by del t. Okay, now the second equation term is del square CA by del x square. So please try this yourself. If this may be slightly faster, but then you should try this as just, product rule and making sure all the terms are balanced. The second thing is del square CA by del x square. By del x square. So again, this is del by del x of del by del x of CA, right? And CA is nothing but theta m by root dat, right? And the first, now t is not a function of x, so only theta is a function of x. So we can simply say this m by root dat comes out, and this becomes d theta by d eta times d eta by dx, or del eta by del x, right? And del eta by del x, as we have discussed, del eta by del x, if you look at this term here, del eta by del x is simply 1 by root dat. Okay, so we will still simplify this further here. This becomes del by del x of m by root dat d theta by d eta 1 by root dat. Okay, now we'll take another derivative, which is with this one. This becomes m by root dat, because there are two square roots, so this becomes the full variable, and this becomes d square theta by d eta square times d eta by del eta by del x, which means this becomes m by dat to the power 3 by 2 del square theta by del eta square. Okay, so please do verify this. I realize this is a lot of product rule. This is what we get for del square c by del x square, and this is what we get for del c by del t. Okay, so just take some time. I have done this a little bit in a rush, but please do try and see that you're able to get this. This is very important. In your homework problem, you have a very similar problem where you have the denominator to be time dependent. So it is crucial. Sorry, the CM like here. So it is very important to be able to know how to solve such problems. So please do try this. Practice this once, and I'm sure you will be able to get it. So now let's compare. So our del CA by del T is, we can substitute in the original equation, is minus m by root 2 dAt times T into d theta by d eta times eta plus theta is equal to dA times this term, because this is del square CA by del x square, m by dAt power 3 by 2 del square theta by d eta square. So what you get now is you will basically have all of these terms cancelled, not the two. You will have all of these. You can check that this gets cancelled because and m also gets cancelled. Or essentially your final equation becomes ODE d square theta by d eta square plus 1 by 2 d theta by d eta into eta plus theta by 2 is equal to 0. Okay, so I know this is a very long way to come about this, but hopefully you followed everything. So now let me repeat. We started with CA by CM. There was no maximum concentration scale, so we took that as to be root DAT from the mass by root DAT from the the order magnitude analysis of the integral equation, and the penetration depth remained the same. So then when we went to do it, we had to apply product rule also because CM was the function of time, so it became slightly longer. But you apply on both term, del C by del T and del square C by del X square, and then you compare and you got an ODE. And the nice thing about this ODE is there is no time dependence or X dependence carrying around. That means our similarity transform was actually successful. Now the boundary conditions. Now this is a second order boundary. So second order condition, and this is the boundary condition. And what we do is we have theta at x is equal to C is at x is equal to infinity is 0, which means just eta at infinity is 0. And del C by del x is simply d. So del C by del x is simply, as you can see, del C by del x is d theta by d eta. So you can verify this essentially that theta at eta equal to infinity is 0 and d theta by d eta equal to 0 is 0. So these are our two boundary conditions you want to solve. One thing we have not done till now is make use of the integral equation, and that I'll come back in a bit. Okay, so let's start with here. All right. So we have this equation. How do we solve this? So this is one of those cases where you have to be slightly more experienced to spot these things, but it becomes a habit to you if you have done this a few times. So I can just give it to you how you can see that this essentially is because you have eta d theta by d eta times theta. You can see that it's like a product rule of eta theta by 2. Just think about it. Eta times d theta by d eta plus theta is the product root of this, and this is simply the derivative of this. This is equal to 0, or d theta by d eta plus eta theta by 2 is equal to constant. So that's the first integration. And if you do that, essentially what you get is when you apply put theta equal to d theta by d eta to be 0, when you use this boundary condition, you get this constant is equal to 0, because when eta is 0, d theta by d eta is 0. So this is equal to 0, this is equal to 0, and so constant is also equal to 0. Okay. Or second, so equation becomes d theta by d eta plus eta theta by 2 is equal to 0, or minus d theta by theta is d eta by 2. To verify this, I'm just rearranging the equation, or minus log of theta is eta square by 4 plus some constant. It's and then I'm sure you must have all done these kinds of math steps, that the logarithmic you can convert into exponential, and the constant then becomes something we don't know. This constant a. So we get this theta to be this profile, exponential a into exponential minus eta square by 4. And now essentially what you get is, now we should use the second boundary condition to phi a. But when I put eta equal to infinity, I already get theta equal to 0. So I still haven't found this constant a. And that's where we will go back to this integral equation, because we still have one condition left that we have not satisfied, which we need to satisfy. So the second boundary condition is automatically satisfied. So we'll go back to the integral equation to find A. Use integral equation to find A. Okay. All right. So let's find. So what is CA? CA is theta into m by root dAt. Or I think it's the opposite. Let me check what is CA is theta into m by root dAt. Okay. So theta times m by root dAt, or which means theta is a into exponential of minus eta square. Eta square is x square 4 by dAt into m by root dAt. So this is our final equation. We still want to know the value of a. So this is what we get for CA. Now let's substitute this in the integral equation. Minus infinity to infinity. CA dx is equal to m, or this becomes minus infinity to infinity. A is outside. A m by root dAt is outside. A m by root dAt. This becomes exponential of minus x square by 4 dAt. Dx is equal to m, right? So this is our equation. M gets cancelled here, you can see, right? And this integral, you can basically, this was something which we had discussed in class 2, but this is equal to root pi. This is a very standard result. So to do that, we will basically substitute x by 2 root dAt as y. So dx becomes dy times 2 root dAt. Okay. And this becomes substitute here. So because we want to make the use of this result, or m times root dAt minus infinity to infinity exponential of minus y square 2 times dy times root dAt is equal to 1. So this dAt gets cancelled, or we get 2a minus infinity times to infinity exponential minus y square dy is equal to 1. Or finally, we get 2a times root pi is equal to 1, or a is 1 by root 2 root pi. Okay. So I know I'm rushing this. I'm very well aware of that, but I wanted to show you the procedure because there is some mathematical steps. So we basically can do this substitution to get A, and finally this will allow us to write the full solution for CA, which essentially becomes m times A is the A is 1 by root 2 pi. So this will become root 2 pi dAt exponential minus x square by 4 dAt. Okay, so this is our final equation for x, CA, as a function of both x and time. And note that when you put x is equal to 0, we get something of m by root dAt, but there is a prefactor of 2 root pi, which we did not have from our scaling analysis. So you see, Cm here comes out to be m by root 2 pi dAt, exactly. But from our scaling analysis, we had gotten m by root t, m by root dAt, sorry. So it wasn't too bad, just that the prefactor was off, and that is something we have been able to find from the exact solution. So now, basically the whole exercise is that sometimes in some problems, we do not know the concentration scale or the temperature scale. And in such cases, we have to make use of integral equations or boundary condition to essentially come up with that scale. And that scale is usually a function of time. In this scale, this Cm was a function of time. And because that Cm was a function of time, what we did was that we then, when we were doing the partial derivatives, we had to differentiate both of those terms and get an equation. Then it's all about mathematically solving them. So what I would recommend, because this was a lot of math in a short amount of time, what I would recommend is pause the video at different intervals. Take your time, derive it yourself, and convince yourself that you're able to get this. And once you're able to get this, the homework problem should be very straightforward once you are able to do this. Okay. So I just wanted to make sure I give you a hint for homework and also, expose you to this problem. And you can see this is a very nice Gaussian function that has come out. And if you recall in your homework one, I had given you this profile and I had asked you to verify that it actually follows the unsteady diffusion equation. So now we have actually derived the equation directly from first principles. All right. So please feel free to let me know if there are any questions. Again, I realize this was a bit rushed, but I hope you got the idea and the main, main method to approach the problem. And I look forward to seeing you in the next video.